in this problem, we're going to combine everything we've learned into basically one problem where we look at some experimental data and then we look at some possible mechanisms and we try to see how the two topics will correlate with each other. So the experimental data that we have are going to be basically initial reactant concentrations where the rate has been measured, and then we've got three hypothetical mechanisms, and we're going to solve each one, and what we're going to do is we're going to see which one actually matches up to the experimental rate law. So to get started, we're going to try to solve for the exponent x, and when we do that, we're going to want to use two experiments where only the concentration of NO2 is changing. So the concentration of CO is going to stay the same. So for this, we notice that experiments 1 and 2, the concentration of NO2 changes, the concentration of CO stays the same. So for this particular one, we're going to use experiments 1 and 2. So the next step is going to be to write rate 1 over rate 2, like is shown here. And when we do that, we can immediately cross out the rate constants because they are constants, so they are going to stay the same between the two experiments. And the other thing that is the same is the concentration of CO. And so we will cross that out as well. So now we're just going to plug in the variables and solve for x. So after using some algebra, we can solve for x, and we see that x is equal to 2. Next, we want to solve for y. When we look at y, that's the exponent on carbon monoxide, we're going to look for two experiments where only the concentration of carbon monoxide changes. So we're going to look at experiments 1 and 3 because in those two experiments, the concentration of CO changes, but the concentration of NO2 does not change. Now, this one's actually really easy to solve because if we look at the rates, we see that when the concentration of CO is increased, the rate stays the same. You can see it's 0.144 molar per second in both experiment 1 and 3. And so what that means is that it means that the concentration of CO has no effect on the rate of the reaction. And so in this case then, that means the exponent y is equal to 0. And that's because anything to the 0 power is equal to 1. And so the concentration of CO is going to have an exponent of 0, which means it's 0th order with respect to carbon monoxide. So that means then that the experimental rate law is just going to be simply rate equals K times NO2 squared. So now we can look at our plausible mechanisms. And if we just look at mechanism A, we can see that the rate law for that one would just be rate equals K times NO2 times CO. And we can see that that does not match up with the experimental rate law, which is just K times NO2 squared. So mechanism A is out. For mechanism B, we're going to consider that the rate law for the overall reaction is going to be the rate law of the slow step right here. And so for that one, it would mean that the rate law would be the rate equals K times NO2 squared. Now, this does match up with the experimental rate law, and so that's a possibility. For mechanism C, we're going to consider that the step 1 is going to be fast and therefore reach equilibrium, as is indicated by the double harpoons here. And step 2 is going to be the slow step. And so when we write the rate law for step 2, it's going to be rate equals K times NO3 times CO. And of course, NO3 is an intermediate, and we can't have intermediates in the rate law that don't appear in the overall expression. So we're going to have to use some algebra to solve for an expression for NO3 that we can then substitute back in. So by the definition of equilibrium, we're going to know that the rate of the forward reaction, that is rate 1, equals K1 times NO2 squared. That's going to be the rate law for the forward reaction. It's going to be equal to the rate for the reverse reaction. So that's going to be called rate minus 1, and we'll use the variable K minus 1 for that. And so the rate minus 1 is going to be equal to K minus 1 times NO, as it appears here, times NO3. And so this is going to be the rate law for the reverse reaction. So these two rate laws are essentially going to be equal to each other because the rate of the forward reaction is going to equal the rate of the reverse reaction when you have an equilibrium situation. Now what we're going to do is use that to solve for an expression for NO3 that will allow us to substitute back in to the rate law for the slow step, and then we can get an expression that does not have an intermediate in the rate law. Okay, so at this point we've solved far enough, and what we can tell is that no matter what we do here, the rate law for the slow step is going to have the term CO in it. And so because of that, and because we know that according to the experimental rate law, the exponent on CO is a 0, what we can tell is that the correct mechanism, according to our experimental data, is going to be mechanism B.